All right, today we're diving into a really cool and honestly elegant class of generative models called Normalizing Flows. They have this unique superpower that a lot of the more famous models just don't, and understanding it really opens up a new way of thinking about AI. So let's jump right in.
So, you've seen AI generate these stunningly realistic images, right? A face, a landscape, you name it. But what if you flip that around? What if you show an AI a new face, one it's never seen before, and ask it, how statistically likely is this face based on everything you've learned? Well, for a lot of generative models, the answer, surprisingly, is they have no idea. And this is where the difference really becomes crystal clear. You've got famous models like GANs, Generative Adversarial Networks, and they're absolute wizards at creation. They're amazing at generating new data, but they have a massive blind spot. They just can't tell you the probability of any given thing. Normalizing Flows, on the other hand, they can do both. They can generate new stuff, and they can give you an exact mathematical likelihood for any example you hand them. And that is a total game changer.
So, how on earth do they pull this off? Well, the core idea is actually beautiful in its simplicity. Instead of trying to learn a super complex data distribution from scratch, a normalizing flow starts with something really simple, like a basic bell curve. It then learns a whole series of transformations to carefully stretch, bend, and warp that simple shape into the complex distribution it's trying to model, like, say, the distribution of every possible human face.
To really wrap your head around this, we need to think about it almost like a sculptor working with a piece of clay. It really is all about stretching and squeezing.
Okay, so everything begins right here, with what we call the base distribution. Just picture a perfect, predictable shape, something we know inside and out, like a standard normal distribution, that classic bell curve. We can easily grab a point, a sample, from anywhere on it. This is our raw material. Next, we bring in a mathematical transformation, a function we'll just call f. This function's job is to take a point z from our simple shape and map it to a brand new point x in a much more complicated space. You can literally think of this function as the sculptor's hands molding that simple lump of clay into a detailed sculpture. And this leads us to the key insight. Just like with that ball of clay, the total amount of probability has to be conserved. It can't just disappear. So if our function stretches out a region of space, the probability density there has to get thinner. And if it squishes a region together, the density has to get thicker. Nothing is created or destroyed, it's just rearranged. This makes generating a new image a pretty straightforward two-step process. First, you just grab a random point z from your simple base distribution. Second, you push it through your learned transformation f, and bam, out the other side comes a new complex data point x, like a totally realistic photograph. Okay, so generation makes sense, but this still doesn't explain that other trick, right? The probability calculation? To do that, these models need a very special property, a kind of secret weapon.
This is the million-dollar question. If I give you a complex thing, like a photo that already exists, how can we use this setup to find its probability? How do we run the movie backwards?
And here it is, the big secret. The function f has to be invertible. What that means is, for every single output x, there is one and only one input z that could have possibly created it. It's a perfect two-way street. You can go from the simple space to the complex, and you can always find your exact way back home. Let's just put some names on these directions to keep things clear. This forward path, going from our simple variable z to our complex data x, we call that the generative direction. Pretty straightforward, right? It's how we generate things. Now, the inverse path, going from a complex x all the way back to its simple origin z, that's the normalizing direction. And hey, that's where the name normalizing flow comes from. It takes a messy, complex piece of data and normalizes it, turning it back into a simple point on our standard distribution. This is the key to calculating probability. So let's walk through it. To find the probability of a photo x, we first pass it backwards through the inverse function to find its unique origin z in that simple base distribution. Now, since we know everything about that simple shape, we can easily look up the probability of z. The final step is we just have to adjust that base probability by a factor that accounts for how much our function stretched or squeezed the space right around that point. And just like that, you have the exact probability of your original photo. It's incredible. So that's the theory, and it's really beautiful. But in practice, one single mathematical function just isn't powerful enough for complex stuff like generating faces. So let's see how this concept is scaled up to build a full-on machine learning model. Instead of trying to create one giant complicated transformation, we get clever. We use a deep neural network where we stack a whole bunch of simple, invertible transformations one on top of the other. Each layer makes one small, reversible change. The data literally flows through these layers, gradually morphing from a simple bell curve into a complex distribution. Or, you guessed it, vice versa.
Now, for this whole chain of transformations to actually work, each layer has to follow 4 really strict rules. It's got to be expressive, powerful enough to help model complex data. It absolutely must be invertible, like we've been saying. And here's the practical part. It has to be efficient, both computing the inverse path and calculating the determinant. That's the fancy math term for our stretch and squeeze factor. Both of those have to be lightning fast. If they weren't, training one of these models would take forever.
To meet all these strict rules, engineers have come up with some brilliant architectures. A really popular one is the coupling layer. It uses this amazing trick. It splits the data in half. The first half just passes through totally unchanged, but it's used as a control panel to decide how the second half gets transformed. Then, in the very next layer, they swap roles. This you go, then I go approach is just an ingenious way to build a transformation that's both powerful and super easy to reverse. So, we've got the theory, we've got the basic architecture, but what's the payoff? What can we actually do with all this out in the wild? Well, let's look at some of the really powerful applications. Of course, the most eye-catching application is generating incredibly high-quality images. Big-name models like GLO are built on these exact principles, stacking layer after layer of invertible transformations to turn simple noise into complex, totally believable photographs. That perfect two-way street also lets us do some really cool things, like interpolation. Imagine taking 2 photos of completely different people. You can run both of them backwards through the network to find their unique starting points in that simple latent space. Then you can just trace a line between those 2 points and feed all the in-between values forward through the network. The result? A perfectly seamless, realistic morph from one face into the other. And this brings us right back home to that unique superpower, calculating exact probability. This makes normalizing flows fantastic for anomaly detection. You can train a model on what normal data is supposed to look like, say normal medical scans or legit financial transactions. Then, when a new piece of data comes in, you calculate its probability. If that probability is astronomically low, you can instantly flag it as a potential problem, an anomaly that a human needs to take a closer look at. So, at the end of the day, normalizing flows are so much more than just fancy image makers. They are powerful density estimators. They give us a unique window into the deep probability structure of data, giving us the power to not just create, but to actually truly comprehend. And this all leads to a fascinating, kind of mind-bending final question. The theory suggests that these models can learn to represent any probability distribution. So as they get more powerful, more efficient, what are the complex systems we're going to be able to finally model and understand? The chaotic patterns of the stock market? The intricate dynamics of our climate? Maybe even the very structure of the human brain? The possibilities are just staggering to think about.